Hello, everyone. We're trying to talk about the pole flip here. And I keep trying to talk about the pole flip, but I keep getting distracted along the way. And for those just joining us, I was just talking about this concept of the salt bridge and how that's going to apply when we come back here to the Earth. We attempt to, well, let's just give you the rundown. We got a lot going on here. We're going to start off with Pangea Earth. Over here, we're going to throw the moon at the Earth so we can come over here to our map, see that we have this scar over here. We're going to come over here, we're going to zoom in, we're going to see that this over here happens to be similar in scale to something of the sort. When you trace this circle out and around, it's about a relative proportion to our moon, somewhat similar. And then you zoom back out, and then you happen to notice this whole scar in this region, and then this circle over here is resisting this. And then we came over trying to figure out which ways to throw the moon at the Earth to maximize the amount of energy we can get out of the equation, to see if we can come over here to our map and take all these land masses, start off from this, and turn them pretty much into what we have here in one single event. And while we were doing this, we happened to stumble across a unique arrangement where you have the moon orbiting a different celestial object than the Earth down here. The Earth is coming in around here, it's coming in around here, and the moon up here is coming in around here and coming in around here. And as these two might have made a closer approach to one another, they don't even have to cross paths, but when this comes in from around here, you have this coming in from around here. So they meet almost in a head-on collision. But we already explained that before that ever happens, before that can take place, the distance between the two objects decreases, and then you get a spark, and then you get features like this on our Earth, and stuff like this very distinctly on our planet. And then you come back over here to the right hand rule, and it makes sense because you can come over here to the spark gap and you see that if the electricity is flowing in this way, the force of motion is going to go this way. And if this object was coming in like this and now it has to redirect like that, it makes sense. And plus you have Faraday's law of induction, where the flux in the magnetic field is going to cause the electrical current. And we looked over here to our equation where we started off. We wanted to maximize the amount of power we can get, and we realized this way you have this in this equation, you have this coming in around here, and then you have this coming in around here. Now you have, if the Earth steals the moon from this, you have the demand to balance charge between this potential and this potential, which packs a lot more amperage into our equation. We realized we could tidally lock the moon almost in an instant, and then we came back over here to our Earth, and we noticed that there's these features right here, and then there's this demand to balance the charge, and then it all started to make sense. So what is a pole flip? That's the question we're going to go into. Before we get there, what caused the poles to flip? They don't really tell you, but they make up stories, and they kind of scare people about this one a lot. You get a couple numbers. 41,000 years ago for frame of reference. Down here it says 7,800,000 years ago was. But they don't really explain what I asked, what caused this. So you come over here to geomagnetic reversal, and we take a look at this, and we're scrolling down here, and this gives you an idea. This is one direction, this is another direction. We scroll down here, and this is like extended time, I guess, but this kind of just looks like a barcode to me, and really what you see is a frequency. What is a frequency? And we come over here, and we see that. And when I think of a frequency, I think of alternating current. When we come over here to alternating current, we're going to look at this. Let's see. This is back in the 1880s. Thomas Edison and Nikola Tesla. This is a battle going on here. One of these two guys invented AC current. Anyone want to guess who that was? I remember learning about this guy. I never really learned much about this guy. We should talk more about this later because like just the suppression of him alone is like a tell right there in my mind. But yeah, it looks like Nikola Tesla is the guy who invented alternating current. Back in 1893 this was. So, what is alternating current? Periodically reverses direction and changes magnitude. And, okay, so when I come over here, and I see this, and I see a frequency, and I look at my right-hand rule, we have this known relationship between electricity and magnetism. I come over here to the Earth. I come over here to the spark gap. We're right about here. I come over here to our orbit. If we just stole the moon, and there's this demand to balance between these two potentials, and there's all the stuff that's happening between the Earth and the moon. Salt water happens to be conductive, but more importantly than the salt water, what you have is a scenario where the distance between these two objects, you now have the Earth in the middle of it, and it's going to be larger than the moon. So I think this took place, looks like, across the surface of the Earth while this was all happening. Haven't talked much about it, but it really looks like Antarctica was being pulled down as this was going on. You see a lot of this rushing in here. This area, it's kind of coming in. And the electricity, it wouldn't flow through the object. It's going to flow across the Gaussian surface. But if there's like a fracture here that when you start off with Pangea and you hit it with the moon and then it like these bulge out, this kind of comes back over, shapes itself a little more cohesively, and you come over here and you look at these volcanic islands and this over here, and this is a sprite, how I see it. But then you have this going on here. There's even the more reason gonna want to charge from this side of the planet is gonna want to balance because of what's going on here. And if this is temporarily disrupted, then you can see why a flow like this might happen, where it's curling up and around in here, and it temporarily stops, and then whenever this stops, you get the electricity kind of flowing from one side of the globe to the other. But I also kind of want to talk about, so why didn't these guys figure that out? And why are they scaring people? Because that's like 1893. And here we are in 2023 now, and these people still don't know. Anyone want to give me a rough estimate at what the budget is to just study this? And you can find like countless articles on this, but no answers. But they're all applying the uniformitarian mentality to this. When they see this, they're looking at hundreds of thousands of years. This is like billions of years to them. But if you come back over here on the map, and then you come over to your right hand rule, you come over to this map. Let me double check this here. Yeah, we're right here. Double check. Yeah, there's still the need to balance the charge between these two potentials. So yeah, no, we're still right here. We have this. We've known about alternating current since. Come over here, still the demand. We got everything seems to fit. Looking at it like that. Am I missing anything? Anything? These guys apparently are. Nobody thought of alternating current. Oh yeah, well, that's what happens when you destroy the impartiality of the neutral observer long before they ever get out into the field. They see this, they think hundreds of millions of years. They come over here. It's that distance. It moves like very slowly now. And what? What else is there? Did we just? No, Nikola Tesla just figured out the pole flip. Like 130 years before the scientists did. Is what I see here. I don't know. Let me know if anybody sees it different. I'll make another video and we'll talk more. Take care, everyone. Thanks, Nikola Tesla.